All right, pre-calculus honors, let's get ready to rock and roll. My daughter was up like 3 times last night, so I didn't get really any sleep. So I figured, why not, make like a couple of, videos. So sorry if I'm not as crazy and, as engaging as usual. Anyway, so we've been talking about the definite integral, okay? Really spoke about 2 things with the definite integral. One, that the definite integral can represent the area between a function and the x-axis, okay? That's not necessarily always true. Sometimes the definite integral could be negative, and we know that area actually can't be negative. We really will speak about that more next year as opposed to this year, but, something to think about. And then we talked about, actually evaluating the definite integral. Okay, something like number 5 should be a piece of cake for you at this point in time. Make sure you actually know how to integrate, all right? So if you slacked off last chapter, still sent in the assignment after, staring at your notes or somebody else's notes, it's all about learning, okay? Not about the grades you actually get. So make sure you know how to integrate. Make sure you plug in that upper bound first. Subtract the plug in the lower bound. We've discussed why that's actually the case. So number 5 and number 6 should have been good. Number 6, you instead of using u substitution, okay, remember we talked about u substitution with the definite integral. Now it really becomes tres substituciones, because you need to substitute for 3 things, all right? What you substituting out for u, you need to substitute out the dx, and then you need to change the bounds as well. Remember, if you put bounds of -1 and 1 right here, you're incorrect, okay? This du implies that these bounds represent u values. And some people are like, well, you know what I mean. I got the right answer in the end. That doesn't matter, okay? It's about the actual process you go through to get that answer. You will lose points on the AP if you put a -1 and a 1 right there. Obviously, if it's a part 1 problem, you won't lose points as long as you get the right answer in the end. But that's not the proper way to train you, okay? It's not what this class is about. The dx right here implies that these are x bounds. All right, so make sure if you perform u substitution, you change the bounds as well. Should be a pretty easy problem. You could have avoided u substitution by double bubbling this thing and actually double distributing it. Then it would be basic integration. So lots of ways to do these problems. It's not just going to be one way. Number 7 is really cool. Okay, the integration should be doable. People do struggle with it because of the u substitution. Little chain rule action right here when you take that derivative. Changing those bounds. The cosine of 2 times 0 is the cosine of 0, which is 1. The cosine of 2 times pi over 6, all right? Cosine of 2 times pi over 6. Well, 2 times pi over 6 is just pi over 3, right? So the cosine of pi over 3, which unfortunately, you do need to remember is equal to 1/2. Okay, things that we spoke about. Don't get calculus problems wrong just because you don't know your trig, y'all. And I don't know if you noticed it or not, but this is the first time where we suddenly have a situation where the lower bound is greater in value than the upper bound. This actually means you start at u equals 1, and then you integrate backward to go to u equals 1/2. You could do that. We'll do it conceptually next year all the time. Right now, you don't have to worry about anything, okay? You just want to integrate like normal, which might bother you, okay? You end up with 1 over, Mr. Harrington's favorite band with these 2 things reversed, right? If it was U2. That old fossil. Anyway, so we got 1 over 2u right here. When you evaluate the definite integral, please plug in the upper bound first. 2 times 1/2 is 1. That's the 1 over 1. Then subtract the plugging into the lower bound. 1 over 2 times 1 is going to be 1/2. Don't be like, well, this number's bigger, so I should plug it in first. No, this guy's the upper bound because he is position that he's in, okay? If there's a bigger number up here, like over here, this isn't the upper bound, this 2, because it's a bigger number. It's an upper bound because of where it's placed on the integral sign. So still, you do end up with a positive value here, you might notice. Sometimes you might notice when the bounds are not in order, you get a negative value. There are different things that are going on that we're not really going to discuss right now. So just integrate like normal, okay? But I don't know if you noticed that or not. If you did, kudos for you. 8 could be a nightmare, okay? The integral from 0 to 1 of e to the 2x minus 1. See, at first it's not bad because you're like, this is easy to integrate. U is equal to 2x right there. Then you get e to the u. But what you have to be careful of over here, when you pull out that 1/2, the integral of e to the u with respect to u is going to be e to the u. The integral of 1 with respect to u is not x. It's u, all right? And that's very difficult. I get that. That bothers people. It's not something you really see all that often on the AP exam these days, all right? But there are still techniques that you need to know. What the heck was the problem? The integral from 0 to 1 of e to the 2x minus 1. You can actually avoid the u substitution piece because having to integrate that 1 and get a u back really bothers people. But to avoid it, you need to integrate mentally, okay? And this is very dangerous to do, but this is probably the best situation to do it in when you have e raised to a linear. Remember, if you integrate e to the 2x, we know we're getting e to the 2x back. But now you have to understand that use substitution is like chain rule for integrals. Chain rule, you multiply by the derivative of the inside. Integrals, you divide by the derivative of the inside. The derivative of 2x is 2. We'll divide by 2 minus, now the integral of 1 with respect to x is going to be x, and we'll evaluate this from 0 to 1. We won't have to change the bounds, okay? If you integrate mentally, you don't have to change the bounds. Plug in the 1, e to the 2 times 1 over 2 is e squared over 2 minus 1. And just be careful here. People are like, yeah, I love zeros bound. You always get 0 back. Not in this case, okay? If you plug in this 0 right here, you get e to the 0 over 2 minus 0. And e to the 0, remember, that's equal to 1. So you actually get e squared over 2 minus, I'll write the 1 as 2 over 2 if you don't mind, minus 1 over 2. All right, and that gives us e squared minus 3 quantity over 2, okay, which I think is the same answer we got before. Yeah, same thing, okay, if you distribute that 1/2, or even if you just put the 2 under there, instead of multiplying by 1/2, divide by 2. So mental integration has its advantages, okay, can help situations out, not so much because the u substitution is difficult here, because of that 1. You can also split this into 2 integrals if you want to. You got to play around with this. There's not one solid way really to do most integrals. A lot of them can be done in many different ways. And you have to practice, okay? It's extremely important. Then we'll kind of jump right back into the conceptual graphical thing right here. Suppose they want you to find the area of region. It's a pirate's favorite region, right? When his first mate was looking through his telescope and he's like, there be boats out there. And the captain turns to him and he goes, arr. He was really correcting him. There are boats out there. That's where the whole arr thing came from. Why are pirates so cool? I don't know. They just are. Anyway, so here, we want the area of this region. And remember, if you want the area between a function and the x-axis, you want to integrate that function. The problem is when we get right here, at x equals 2, right, because that's the point 2 comma 4, you might notice that to get the area from 0 to 2, we want to integrate x squared, right? It's the area between x squared and the x-axis. But then from 2 up to whatever the heck this value is right here, we'd want to integrate negative 2x plus 8, because we want the area between him and the x-axis. The moral of the story is, this job cannot be accomplished with simply one integral. We need, very good, 2 integrals, okay? And the first one's going to be the integral from 0 to 2. Second one's going to be the integral from 2 up to. I wonder how I get that root right there, that 0. Oh, function always represents y values. And if you want to know where a function's equal to 0, you set the function equal to 0. That's how you get the 0 right there. So 0 equals negative 2x plus 8. So what would x have to be equal to here? 4. Okay, so I know that that's actually going to be 4 right there. So when I set up my 2 integrals, I'm going to say area equals A. It's Fonzie's favorite letter. A. Maybe your parents get that one. Let's do the integral from 0 to 2. And that's basically to get this area right here, we want to integrate y equals x squared from 0 to 2 with respect to x. And then we're going to take that area, we're going to add it to this other area, okay? The integral from 2 to 4 of now negative 2x plus 8, okay? The integral from 2 to 4 of negative 2x plus 8. This right here, looking at it, it's disgusting, okay? Obviously, you need the dx right here, because otherwise it's incorrect. And right now, it's incorrect as well, because the dx only applies to the 8. You need to apply to the negative 2x as well. It's important to have these things set up the correct way. Be very, very careful. How is that? Is that set up okay? Thumbs up, thumbs down, sideways thumb. Email, send me a reminder if we need to. Today is Thursday, this ditto. Am I doing a Google Meet today? I don't know. I think I'm going to do a Google Meet at some point this week. Maybe it already happened. I don't know. Hey, anyway, so here, let's have some fun. Integrate x cubed, add 1 to the exponent, divide by that number. It's evaluated from 0 to 2. Some people are like, well, I don't really remember how to integrate. You're done, Poppy. Let's go. Get on the ball. Here, integrate negative 2, x to the first. So pull the negative 2 to the side. Integrate x to the first, x squared over 2, plus the integral of 8 with respect to x. That's somebody's derivative in there. Whose derivative? 8x's derivative. I was so hungry, I ate x. Stop talking about your x, okay? And we're going to evaluate that one from 2 to 4. Obviously, this is just really negative x squared right here. So here when I evaluate, look at this, evaluating 2 integrals at once. What, are we crazy? If I plug in the 2 cubed, that's 8/3. Minus 0 cubed, 2 cubed over 3 is 8/3. Minus 0 cubed over 3, that's 0. Bring down the plus sign. You don't have to show you're plugging in each number separately. Start skipping steps when you get good, but you don't have to skip steps right away. Be careful over here. When I plug in the 4, I get the negation of 4 squared. That's negative 16 plus 8 times 4, which is 32. That's the upper bound, right? And we're going to subtract from that the plugging into the lower bound. If you plug in a 2, the negation of 2 squared is negative 4, plus 8 times 2 is going to be 16. You could put a set of brackets around this if you want. Not necessary right here, but it kind of like represents that this is the entire integral that we're doing, the second integral. This is a minus sign. It'd be very important to put brackets here so you could distribute the negative. Really easy to make silly mistakes and stuff like that, so try to be very, very careful. Here we have 8/3, minus 16 plus 32. Don't forget to distribute this negative, okay? Plus 4, minus 16. You could also combine these if you want, get what those answers are, then subtract them. Billions of different ways to do it. But this is kind of sweetness because negative 16 is negative 32, which cancels with the 32. So it's really just 8/3 plus 4. It's supposed to be 8/3. You see how the top of my 3 became the fraction bar right there? Weird stuff. 4/1 multiplied by 3 top and bottom, so 12/3. So what does it become? 20/3 over here? It's a lot of bronze medals, 20/3. I think that's funny, okay? I'm sure you've missed my humor at this point in time with this prolonged absence from school. Anyway, so, cute type of problem. Who knows? Will you see something like that again? Will you not see something like that again? You got to be ready for any type of situation in calculus. It's all about being prepared, for many different situations, and then using what sometimes to synthesize an answer to a new situation that you've never seen before, okay? And things like that happen in calculus all the time. As far as today's lesson, let's get a little star action going. What do you think, Flanagan? Give me a little star. Star! He's probably did a good one wherever he is. I heard he practices in front of his mirror at night. Anyway, so let's talk about something known as the area between two curves. Area between two curves. I'm being mean to students today. It's a good thing this isn't being recorded or anything. As far as area between two curves is concerned, very important on the AP exam. Unless you're talking about this year, because this is one of the topics they took off of the AP exam. But I got through it before that. I got through the whole AP curriculum and prepared my students for the AP exam. Hopefully well. Anyway, so area between two curves. It's not always the area between a function and the x-axis that's necessary to get. And these used to be more popular on the AP exam. They used to be insanely popular on the AP exam. They are still popular, okay? Just not quite as popular as they used to be. So I'll draw some kind of function here. Oh my God, that looks horrible. All right, we'll call this y equals f of x. And then I'll draw another function over here. And we'll say this is y equals g of x. What up, g of x? And you might notice there's a region that's been formed between these two, okay? And here we actually want the area of region R. We want the area between these two curves, okay? And you can see this region right here starts at an x value. I'll say it's an x value of A. That's the leftmost x value of the region. And you can see the rightmost x value of the region is this guy right here. We'll call him B. Normally at this point in time, I'd say, hey, how are we actually going to be able to get the area between those two curves? And I'd call on somebody in class, and every year somebody manages to figure it out. And it's really like those old school problems because there's no formula for the area of this type of shape right here. And who knows what kind of shape is going to be formed with different types of curves and things like that. So sometimes you got to go with that old standby area of big minus area of small. You're like, what are you talking about? Well, if you actually do this, if you start with the integral from a to b of f of x with respect to x, think about what that represents. Okay, here's f of x right here. I'll just focus on the portion that's in the region. And you can see if you actually integrate this from a to b, well, then you're getting all this area here, okay? The area between the function and the x-axis. And remember, that's too much, okay? I'm actually picking up this extra area that I don't want. I just want the area of region R. So I need to subtract this area right here, this red area, if you will. And that area happens to be the area between g of x and the x-axis. Do you guys see that right here? Okay, so if you actually integrate g of x from a to b, you'll get this area right here. That's what you want to subtract from this big area, the integral from a to b of f of x with respect to x. So we'll subtract the integral from a to b of g of x with respect to x. And that's going to give me the area between two curves, okay? And it's actually a little bit simpler here because, what you could do is when you see these types of problems, what you could do is remember what the definite integral does. He stuffs an infinite number of rectangles, okay, yesterday between a function and the x-axis or the day before. Here it's going to be stuffing an infinite number of rectangles between a function and a function, getting their areas and adding them all up. So we're going to draw one rectangle, and we're only drawing one, but we're really imagining like an infinite amount, or like 7, something like that. But you can see it doesn't matter where, how many rectangles you actually drew. You'd see throughout the entire region that the upper function is always f of x, the top of the rectangle, and the lower function, the bottom of the rectangle, is always g of x, okay? And that means you could actually set up to get the area, the integral from a to b, of one, you could use one single integral. You could say the upper function, which you know is f of x, minus the lower function, which we know is g of x, and then integrate that whole thing with respect to x. And that's equivalent to what we have up here. Because remember, you could break up integrals over subtraction, but that means you could also put them back together, solid, strong, New York tough. You could put them back together over subtraction, okay? So really, that f of x is the upper function, and that g of x is the lower function. That's the formula you're going to use for area between two curves. What do you think? Megastar! A little megastar action. Here's the real formula for the area between two curves. Area between two curves. Very similar to what we have written out over here, but I'm going to say area is equal to the integral. Instead of a to b, these a's and b's will represent x values. Eventually, they'll represent y values as well. That's something we won't speak about until next year. Or maybe we'll talk about it this year, because I think we got like a little extra week to get some stuff done. I was going to do something else, but I'm just thinking that might be a cool thing to do. We'll see. The integral from, I'll say, x sub 1 to x sub 2, because for this type of problem, they're going to be x bounds. And then you want to draw that one rectangle. And just imagine an infinite amount and be like, throughout the entire region, is the upper function consistent? Is the lower function consistent? And if it is, you could just integrate upper function minus lower function with respect to x, which is what I have right here. Okay, so we like to call this upper minus lower when you're using x bounds. Next year or later this year, we'll use y bounds and we'll do right minus left. Crazy stuff, I know. But let's actually, put this into practice. What the heck is the crazy old bold guy talking about? Let's go to that integration packet that we've been using since the first day. I think it's like 5.1 integration packet, something like that. Find the area of number 12, and we'll do no calc on this one. Yeah, no calc. Who needs a calc? All these slackers like Kayla Allers. Just kidding. Hey, find the area of the region bounded by the curves y equals 3x plus 7 and y equals this quadratic right here. And at least I graphed it for you. And some people might be like, well, with no calculator, how do I know which curve is which? That's a problem, okay? You can see that y equals 3x plus 7 is going to be the linear. The linear! People get mad. They're like, you can't say a straight line is curved. You can call a straight line a curve, just so you know. It just has zero concavity. It actually means the second derivative is equal to 0. It's neither positive nor negative. More on that next year. Hey, and then you know that this guy's got to be the quadratic. It's a quadratic. X squared plus 2x plus 1. And look, this is the area between two curves. You can see this region that they're talking about, okay? It's not the area between a function and the x-axis. It's the area between a function and another function. And whenever that happens, you could draw in a sample rectangle, a vertical rectangle. There's also horizontal rectangles that you could draw in, but that's for a right minus left situation, which we won't talk about this chapter. Vertical rectangle, and think about it. You're only drawing one, but you're really imagining like an infinite amount. Like 7 would be enough. But you can see no matter where you draw that rectangle, the upper function will always be the linear in the region, and the lower function will always be the quadratic. Believe it or not, things like that change, okay, in certain situations. We're doing easier problems today, but if you see that, if you see the upper function's consistent, the lower function's consistent, you can use upper minus lower to get the area, okay? And the upper function we know is the linear, that's 3x plus 7. Check this out. Minus the lower function. The lower function is the parabola. Imagine you did this. Yeah, minus x squared plus 2x minus 1 plus 1. I'm smart. Look at me. Doodly-doo, doodly-dee. No, you're not. What'd you mess up? Everybody screaming out. Screaming out. I want your parents to be like, why is my son or daughter screaming parentheses at the top of their lungs? All right, we need those parentheses right there. I've been speaking about that since the beginning of the year. Now, technically, if you put the dx, you're actually wrong because it only applies to this guy right here. You need another set of parentheses or a set of brackets, whichever you wish. And that's actually your upper function minus your lower function. Then you need the bounds, okay? And you want to think about for the bounds, x bound to x bound, the leftmost x value of the region to the rightmost x value of the region. Bounds don't always need to be in numerical order, but they usually are when you're setting up the integral yourself. When you're really good, you can start really futzing around with that. But for now, think about it. The leftmost point of this region is right here. Here's the leftmost x value. That point has an x value of -2. And the rightmost spot in the region is right here. And that point has an x value of 3. That's why I'm going to integrate from -2 to 3. Maybe they just want the area bounded by the two curves in the first quadrant, which means it's implied that your lower bound would be equal to 0. So it's not always x coordinates of intersection points. Sometimes it is. If you want to do this old school, if they didn't tell you the intersection points, you'd have to set these two functions equal to calculate the x values and the intersection points. That's a little antiquated these days, but it's still something you're supposed to know how to do because, as an advanced placement calculus student, which you'll be next year, many of you, you're supposed to know how to actually, do algebra. Anyway, so before we integrate this thing, simplify it. 3x plus 7 was that minus x squared, minus 2x minus 1. Some people are like, I just like to integrate separately and then get rid of the parentheses. Well, you're wrong, Poppy. All right, make sure you get rid of those parentheses, then you integrate. So here we got the integral from -2 to 3. I got to tell you, if you're annoyed about those bounds, man, I'm right there with you. What are we going to start with here? The x squared's negative. Let's put him last. So -7 minus 1, that's a positive 6. 3x, -2x, positive x. And then we have our negative x squared right there, all with respect to x. All right, so that's our setup right there. Should make it a lot easier to integrate. Here's the easy part. The integral of 6 with respect to x is what you all want to grow up to be, and you will all grow up to be a success. Okay, plus the integral of x to the first, x squared over 2, minus the integral of x cubed, x squared, which is x cubed over 3, and we'll evaluate that from -2 to 3. And if you're anything like me, which means remarkably handsome, and bold. Look, this is the worst part of the problem for me. Having to plug in that upper bound first, like 6 times 3. How am I supposed to know what 6 times 3 is? I think it's 18. I have my calculator hidden off to the side, so you won't know when I'm using, a calculator here. Anyway, so I got 18, plus here 3 squared over 2. So is that plus 9 over 2? This is kind of cute because 3 cubed is 27 divided by 3 is 9. 9 minus 9. That's the plugging in of the upper bound. Subtract the plugging in the lower bound, which is even worse, right? 6 times -2, -12. -2 squared is positive 4 divided by 2 is 2, so plus 2. And then we have, just be very careful here. You make one little negative sign. People are like, this is beneath me. Why do you take so much time talking about stuff like this? Because a -2 cubed is a -8. And when you subtract -8/3, you really add 8/3. Some people have -8/3 right there. They're going to go through the whole rest of the problem, wasting their time and being wrong. Which, part 2 is not the biggest deal, right? Partial credit. But a part 1, all the points being on. All the points. What's the easy Berto way to do this? Let's see. 18 and -9. We'll combine those to get a positive 9. I'll leave the 9 halves right here because he scares me. -12 plus 2 was that -10. Subtract the -10, positive 10. Then subtract that 8/3. So it looks like we have 19 plus 9 halves minus 8/3. And then you realize your worst nightmares have come true. We need a common denominator of 6. Oh no, how can we do this? Call Mr. Harrington. Hello, what do you want? Mr. Harrington, can you help us out with this problem? No, I'm too busy burning down the rainforest. See you later. Click. He wouldn't even say see you later. He'd just hang up. So here, get a common denominator of 6. Last time I do a video on literally no sleep. 6 times 19 is 6 times 10 plus 6 times 9. So what is that? 60 plus 54, 114. Mr. Harrington's age. Plus multiply by 3 top and bottom, 27 over 6. Minus multiply by 2 top and bottom, 16 sixths. Whenever I get an answer with a denominator of 6, I always end up developing a lisp. Here, this is really 100 and, well, how about this? 27 minus 16 was that 11? What really loud amplifiers go up to. 114 plus 11, that's 125 divided by 6. Biggity bam, there's my answer. Multiple things going on here, right? First off, could you set up the integral? Because that's today's lesson, okay? That's the area between two curves formula right there. We'll practice another one in a minute. Then you need to actually, manipulate down to this algebraically. If you can't do that, don't tell me because it's just going to depress me. Then you got to be able to integrate, which you would better be able to do. We focused on that last topic. Did you? I hope you did. Are you taking AP Calculus if you're doing nothing? I hope not. You're going to fail. And then the hardest part, right? Just plugging in these numbers. Just so you know, on part 2 of the AP, you can leave it like this. Okay, but in this class, on my test coming up, and until we get to the AP exam, I want you to be able to do this work as well without a calculator, because in a part 1, you'd have to do something like that. Let's move on to number 14. Number 14 rhymes with mean, and that's a synonym of Mr. Harrington. You might be like, wow, Berto, you're really making fun of Mr. Harrington, a lot today. How come you're not making fun of Mr. Pushy? Well, the answer to that is I really only make fun of people I respect. So find the area of the region bounded by y equals 2. And y equals x squared minus 2. And people are like, oh no, they didn't even give us a graph here. This is no calc. Mr. Berto, what are you doing to us? Daniela Marchese's like, I don't know how to do anything. Look, it's just kidding. She's totally calm and collected usually. You know how to graph stuff like this, okay? If you can't graph this, and you're like, yeah, I'm going to take AP Calculus next year because, society says I got to sign up for 500 APs. You're going to be in a world of hurt. Y equals x squared minus 2. We know what y equals x squared looks like. Shift it down 2 units. I'm not insulting people taking a million APs. I'm just saying if you're going to do that, be prepared to put in the work for that. Don't be like, well, that's just what people are doing. It's the worst way to go through life, by just doing things because that's what people are doing. I mean, come on. Be an individual. Be unique, just like everybody else. If we graph y equals 2, I'm on fire today. Call the fire department. Here's y equals 2 right here. Now, I want the area of this region right here between these two curves. And you might notice a portion of it is below the x-axis, which freaks people out. They're like, Mr. Berto, I thought we only got area, you know, in the region light above the x-axis. Well, when you draw in your sample rectangle here, and remember, you only draw in one, but you really imagine like an infinite amount, or like 7 or 8, you'll see that it doesn't matter where you draw this rectangle, the upper will always be the constant function, the horizontal line, the lower will always be the parabola, you know, and it is true that a little region is below the x-axis here, but what really happens when you do upper function minus lower function, come on, function always represents what? Y values, right? So really you do upper Y value minus lower Y value. This Y value, no, is 2 right here, right? That's obvious. This Y value, I don't know what it is. Let's say it's like -1, suppose. So 2 minus -1 would actually give you a height of 3 right here. So you'd end up subtracting that negative Y value. It would become a positive answer because you'd be adding. So really, the area between two curves formula will always give you area regardless of where the region lies. The entire region could be down here below the x-axis. It doesn't matter because when you do upper minus lower, you'll always get that positive value. That's the height of the rectangle. The dx is the difference of the x values, just this distance right here. It's called delta x when you want to actually approximate these things using Riemann sums. We might do that in a couple weeks. But that's the dx. And remember that the height times the base, I'm going to give you the area, and then you're going to get the area of all those rectangles and add them up. Number of rectangles will approach infinity. You know, but now we can set this up. So say area is equal to integral. Upper function is 2. It's whatever y equals. Don't put y equals 2. Just put the 2 minus the lower function, which is the quantity x squared minus 2. Put another set of parentheses or a set of brackets. Put the dx. And I need some bounds here. You can see the leftmost point of this region is right here. So I need his x value. The rightmost point of this region is right there. I need his x value. Some people just know what it is by thinking about the algebra in their head. But really what you're supposed to do to find out the x coordinates where two functions intersect, it's not always going to be the intersection points that are bounds, but many times it is. You set them equal. They're both equal to y. Let's generate the x values that correspond to the exact same y value for these two functions right here. Subtract 2 from both sides. See, right now, if you're like add 2 to both sides, take the square root, will you just stop with that nonsense? Hey, you could do it if you remember to take the positive and the negative square root. But why is everybody so afraid of factoring? Common Core has taken away skills that you need to know, and I'm here to give it back. All right, so here, a little tee it up. Tiger Woods, y'all. Tiger Woods, y'all. So we know this is -2, and this is +2 right there. So that's my bounds, -2 up to 2. So you could say area is equal to the integral from -2 to 2 of, I don't know, what's in here? 2 minus x squared plus 2, so 4 minus x squared. And then it's pretty doable as far as, you know, integrating by hand. A little annoying, right, with that bound of -2. Remember that bound of -2 before we didn't really like? This bound of -2 bothers me. You know, it would be so much easier if the bound was just 0, right? So I'm just going to do that. People are like, what are you doing, Bertie? You can just change the bound there to make it a number that's easier. But I can. You know, if you actually do the integral from 0 to 2 of this upper minus lower we have over here, it's not going to give you the whole area, right? That'd be -2 to 2. It's going to give you the area from 0 to 2. And that's this. And you might notice that doesn't represent the whole area. That represents half of the area. So if you get that area right there, you can simply multiply it by 2. And you're only allowed to do this right here. These two integrals are equivalent. You're only allowed to do this because of the symmetry. Okay, so because of symmetry. You know, remember, if you had the graphing calculator and you're allowed to use it, you just put this in the graphing calculator, right? Little math 9, get the answer easily. But when you're doing things by hand, tricks like this can become very useful. Also, they might actually give you a picture of this on the AP and say, which of the following integrals represents the area of the region? You know, big region R here. Maybe this integral isn't here. Maybe this one is, okay? And remember, it only works for the symmetry because these are even functions. You know, don't assume. You know what happens when you assume. It's inappropriate. I can't say it on video, but you know what I'm talking about. Don't assume in a situation like this that goes from -2 to 2. Don't assume that you can just get the area from 0 to 2 and then double it. These two areas are not equal over here. You need that symmetry. They happen to be even in this case, but it could be other types of symmetry if you're integrating over different values. So something cute to think about there. Hopefully that's all right for you. This 2, people are like, what do I do with the 2? Leave them to the side as a constant. Pull them to the side. Integrate 4 minus x squared. Integral of 4 with respect to x is 4x. Minus x squared's integral, so x cubed over 3. Evaluate that from 0 to 2. You actually have choices here. You always have choices. You could distribute the 2 inside here if you want, evaluate the integral, or you could leave the 2 on the outside. I like to leave it on the outside in many situations because putting it in there makes the math more complicated without a calculator. But sometimes it's actually easier to put in there. Maybe this is like 1/2 x. You distribute the 2, suddenly it becomes x. Things are easier. So anyway, once again, it's different for every type of problem. Dropping the 2 first. 4 times 2 is going to be 8. Minus 2 cubed over 3, so 8/3. That's the plugging into the upper bound, minus the plugging in the lower bound, which we love here, right? 4 times 0 minus 0 cubed over 3. Mr. Bushy's IQ. And remember, I only make fun of people who I respect. I'm not making fun of him there. I don't respect him. I'm just stating a fact. So anyway, here we have 2. I'm being ruthless today, man. Times, multiply by 3 top and bottom, 24/3 minus 8/3. So is that 2 times, I don't know how to do mental math, 16/3, which gives us 32/3. So a lot of things going on. The main focus today is to get the area between 2 curves, draw that sample rectangle. It might seem so silly at this point in time. You're like, yeah, Berto, I can just look at it and see what the upper function is and what the lower function is. That'll get more complicated, not necessarily so much this year. Next year, when we finally get into volume, when we take these regions and revolve them 360 degrees around a straight line, then things get more intense. Drawing the rectangle is a very important technique. It's simple now, but do it, okay? Draw that rectangle. If you can see the upper and lower remain consistent throughout the region, you can use upper minus lower. The formula, leftmost x value to rightmost x value, that's the bounds. Upper function minus lower function. Careful with those parentheses. And just setting it up, it's all you really need to know for today, because you already know how to actually evaluate an integral, don't you? I hope so. This is a pretty filthy one, this one right here. They got worse than this, but not much worse than that, believe it or not. Cute little symmetry trick too, okay? Different things in these lessons. There's a lot of things, okay, to speak about in calculus to help you out with doing these problems. Try that homework tonight. One of them is with the calculator. One of them is without a calculator. With the calculator, after you set, I think it's this one with the calculator, after you set up the integral, you're gonna have to use the calculator to actually calculate the intersect point to know what this bound is over here. We'll speak about that tomorrow. What am I pointing at? You can't even see it. It's this problem, I think. To figure out this x bound, you'll actually have to calculate intersect with the calculator. You could also set them equal, actually. It's not bad for this particular problem over here. But if you're using the calculator, you could also just set up the integral and go right to the answer. You don't need to show this work. But if you're not using the calculator, you need to show me work. Okay, so we did 2 without the calc. You'll have 1 with calc, 1 without tonight. And we'll see you bright and early, or whenever you decide to watch these videos. Mañana, en la clase de matemáticas, mañana. I heard it's just a day away. Anyway, this is Mr. Berto signing out. I hope everybody's healthy and safe. And we still got more work to do next week, okay, and the week after as well. Then we'll lighten things up a teeny bit, maybe a little final review, give you guys some stuff to work on your own. And the last week we can use for the summer assignment if you guys want to get started on that, if you want to take AP Calc. Anyway, more on that in the future. This is Berto, and I'll see y'all later.